All right, so let's basically consider an incline like this. All right, so here's angle theta. And let's have the object here, let's say at the top of an incline. Now, one thing I have is this. So if you have an object at the top of an incline, and let's say object here is at rest, means that, you know, it's in static equilibrium. All right, so static equilibrium, that means the object has all the forces in x direction cancel, all the forces in y direction cancel. So basically there is no acceleration and there is no motion at all. So if I'm looking at the forces, then how many forces acting on the object in this case? And what are the direction? Who can help me? What are the forces and which direction?
Friction force going down.
Friction force going down like this?
Going up, sorry.
Yes, going up, that's correct. There you go, so this is the friction force. Static or kinetic?
Static.
Static. What else?
The weight going straight down.
Yes, the weight going straight down.
Normal force going perpendicular to
surface, right? All right, there you go. All right, so those are the three forces acting on the object during the, static equilibrium. So if I put this in a force table so I can, organize them. So I can see that here's weight, here's friction, here's normal force, and then this is my net force. All right, so how would I write then the x component of the gravitational force? So remember, this angle theta, same as this theta over here. How would I write the x component of the gravitational force?
mg sine theta.
Mg sine theta. All right, so that means this one will be mg cosine theta. So now also the signs are important, right? So are they going to be positive or negative? Are both positive, or one positive, one negative, or both negative? What do you guys think?
Is mg sine theta positive and mg cosine theta negative?
Yes, and why is that?
Because mg sine theta is positive because it's going in the natural flow of like acceleration. So you just choose it to be positive, so m1a is positive, and then mg cosine
there is
theta
no
is
acceleration technically.
Oh yeah, it's going to be equilibrium. Yeah, you're correct. And then cosine, isn't it just because it's in the downward direction?
Well, think like this. So when your system is in equilibrium, in a way, it doesn't matter where you take your positive or negative, coordinate system, right? So, but let's say what I will do here, I will take down as positive for x and up as positive for y. So then think like this. If I'm breaking down gravitational force into components, right? So this will be y component, and then this will be the x component, right? So now you can see, right, then the x component is opposite to that angle theta. So that's why it is written in terms of sine theta. Y component is adjacent to that, angle theta. So that's why it's written in terms of cosine of theta. And if I'm taking down as my positive, then technically this is my first quadrant. This ends up my second quadrant. This is my third quadrant. And then this is my fourth quadrant. Because if to the right I have positive, right? So basically my, I change like this, right? Counterclockwise. So that means, first, second, third, and fourth. So like that. And we know that in a fourth quadrant, x is positive, y is negative, right? In the fourth quadrant. Also, if you look at, if I'm taking up positive, so technically if up is positive, see the y component of the weight pointing in the opposite direction where I chose to be positive direction for y. So that's why it's negative. And then the x is in the direction of what I chose to be positive x, which is down the incline. So you can look at it from two different points of view. Why is it positive? Why is it negative? All right. So then static friction acting in a negative x direction has no y component. And then the normal force acting in a positive y direction and it has no x component. Because it's in static equilibrium, this is zero, this is zero. That means forces in the x direction cancel, forces in the y direction cancel, and there is no acceleration. All right. So then in this particular case, what I can get here is this. Equation 1 gives me mg sine of theta minus static friction equals 0. Then equation 2 gives me, normal force minus mg cosine theta equals 0. Right, so those are the two equations you get from the force table. All right, so those are my equations of the motion for this particular example. Now I can then kind of, I understand that what it means is then in the x direction, mg sine of theta is equals to the static friction. That's why they cancel each other. And in a y direction, then mg cosine theta is equal to normal force. That's why they cancel each other. So this is my equation 1, this is my equation 2. Now, for example, then I can use this equation to find a number of things. I can do, a number of things because this relates several things. This relates the angle thetas to the static friction, to the normal force and all of those things. But for example, what we're going to do here is we're going to use this condition, right, the static equilibrium in our experiment to find the coefficient of static friction. So we're going to try to find this guy. Okay. Now let's see what, what to do with that. You can see, right, I don't even see that, coefficient of static friction. Where is the coefficient of static friction right now?
Costatic it's equal to mg sine over n over the normal force.
Mg sine over,
over n, because we have the friction, the static friction is equal to mg sine, and static friction is also equal to mu times the normal force.
Okay. So you are going way ahead. So what I was asking here is, where can I find static friction? Coefficient of static friction. And what I was expecting here is this, to say that static friction is part of the, or coefficient of static friction is part of this equation, right? Where the static friction is equal to coefficient of static friction times normal force. So basically you don't see that because in a way it's hiding right there, right? So I can come back and I can basically rewrite this static friction in terms of coefficient of static friction times normal force. Okay. Because they are equivalent. Static friction is equivalent to the product of coefficient times normal force. Now that I can rewrite the static friction in terms of the coefficient of normal force, and if I try to, rearrange or, find the expression for coefficient of static friction, then I can, work with those two equations. You can do, let's say, a substitution, right, or thing like that. But I showed you the easiest way will be to divide, right, those two equations. So you take these equations and divide because each equation has one term on the left, one term on the right. And you can simply divide. That means I'm dividing equation 1 by equation 2, which means the left side are divided and the right side are divided. And you can see, right, when I divide the left side, which is mg sine theta over mg cosine theta, mg just goes away. And I have just sine over cosine. And what is sine over cosine?
Tangent.
It's a tangent of theta. On the right side of the equation, I have coefficient times normal force divided by normal force. Then I can see that normal force also cancels out. Then what I have here is then I have a coefficient of static friction. Now, tell me this. What do I need about this experiment in order for me to find this static friction? What do I need to measure in order to find the static friction?
The angle.
The angle?
The angle theta, exactly. The only thing you need to measure here, the angle theta. And here's the thing, the angle theta here is what we call a critical angle theta, because this is the theta where the object is right before it starts sliding down. That means what we have here is, imagine this object here is on a flat surface, then you increase the, incline, right? You increase until it starts sliding down. But then you go back slightly right before it goes, starts sliding down, and measure the theta that, right before it starts sliding down. This theta is known as a critical angle, because anything above this angle, the object is going to start sliding down. Okay, that means you have an experiment where object is on the top of the surface. We're assuming that this is basically the maximum angle you can have for your incline for the object to still remain at rest. Because if I increase the angle slightly more than that, then you will have basically the object sliding down. It's going to be speeding up down. So that's what you need. So in order for you to find coefficient of static friction, you need to understand we have to go through the steps and find the critical angle. Okay, and or you can do basically, you can just do the mathematics of all of this in order to find it. So that's basically one part of the experiment today. The next part will be this. By the way, any question about this part? I think we covered this also in the lecture class extensively. So let's look at then the second part. The second part will be this. We're going to take our theta beyond the critical angle. That means we have the theta where the theta here is greater than critical angle. Now, what does it mean about our object? Well, it means that right now the static friction no longer, able to keep the object at rest. So it's not sliding down, because that's the thing. That's the thing about critical angle. Any theta above the critical angle, then object starts sliding down, and basically static, that means the gravity component, right? X gravity component is stronger than static friction. All right, so let's then talk about this. All right, so let me try to get a perpendicular like this. Now tell me this, what are the forces acting on this object now and in which direction? Assuming that theta is above critical angle and object starts sliding down. What are the forces in which direction?
So then there's going to be the force of gravity going to the right on the
Force of gravity like this?
Yeah, on the surface. And then the normal force perpendicular to that one.
So you're saying this is the weight?
No, that was the, because it's above the critical angle, so it's going to start sliding, right? So that's the force at how it's going to slide.
Well, hold on.
Right?
Well, not quite. So you have to understand, if the object is sliding down, there is no force pushing it down. Like there is no applied force pushing it down. So when objects start sliding down, technically who's responsible of pushing, or making the object accelerate down? What force is responsible for doing that?
Gravity.
Gravity. And in which direction is gravity acting?
Straight down.
It's still acting straight down, just like before. So technically then, what force or a component of the force is responsible for sliding it down, basically across the surface? So who's pulling it down across the surface?
mg sine theta?
Exactly, mg sine, which is what? Which is the x component of gravity, not just gravity. That means the one that technically makes it slide down is not some kind of different force. It's still same gravity, but it's just the x component of gravity. And we had this over there too, right? See, this guy is still there too, right? So this is x component of gravity. But the idea in the first part, when it was in static equilibrium, those two, the x component of gravity and static friction force, they were equal to one another. But then here they're not. That means gravity has an x component that is stronger than static friction, so objects start sliding down. And this is something I've seen sometimes, students assume that if the object is sliding down, there's some kind of force in this direction, down incline. No, it's not the case. There's no some kind of new force because it's sliding down. It's not, it just means that gravity now is stronger than static friction. And this is something we saw in the previous lab, right? Lab 5, remember? The gravitational parallel component of gravity, which is basically the x component of the gravity, right? Remember, this was equals to mg sine of theta. Didn't we see in lab 5 that basically as you increase theta, the x component also increases? So that's why as you go beyond critical angle, that means we increase the theta beyond critical angle, that means x component starts increasing and it becomes basically stronger than the static friction force. Remember, static friction force has a maximum value, mu s times n. And beyond this maximum value, it cannot go. So that's why what we have here is, if you're increasing theta, just this x component becomes stronger than gravity, friction, right? X component of gravity becomes stronger than friction, so it starts sliding down. All right, so is it still static friction that we're dealing with if it starts sliding down? What is it then?
It's kinetic.
Exactly, it's kinetic because it's moving now. So it's a kinetic friction. And what else is there?
Normal force.
Yes, there's also a normal force. Now, so technically, again, there are only 3 forces: normal force, kinetic friction, and then the gravity. It just, because gravity is 2-dimensional, it has 2 components, Wx and Wy. It just happened to be now, this x component of gravity is greater than kinetic friction, so the object starts sliding down and speeding up down. So basically, that's the idea. And as soon, by the way, as soon as it starts sliding down, the force of friction changes right away to kinetic from static. That means if I'm looking at a table, so I have gravitational force, kinetic friction, and normal force. Now, the weight is still mg sine theta, positive, y component negative mg cosine theta, because almost nothing changes about this problem in terms of the gravity, right? So let's say then kinetic friction is still negative x direction, has no y component, and normal force is in a positive y direction. And in the y direction, those forces still cancel each other because object sliding down an incline, and I take this direction to be my positive x. But the difference here is, because gravity component right now stronger than friction, now we have acceleration. Right now we have acceleration. Okay. Where before mg sine theta minus static friction equals 0, now mg sine theta minus kinetic friction equals mass times acceleration. Okay. That means what we have here is there is an acceleration that we can, understand that there is acceleration because the gravity component, if you go above critical angle, right? So basically Wx becomes greater than friction, thing like that. Equation 2, we still have then n minus mg cosine theta equals 0. Because remember, right? So because the x component was mg sine of theta, so remember, sine of theta increases when theta increases. Sine of theta increases when theta increases. So that's why x component of gravity also increases. But normal force, which is equals to mg cosine theta, starts decreasing, even though this depends on theta, is decreasing because cosine of theta is decreasing when theta is increasing. right? Cosine of theta is, cosine of 0 is 1, but cosine of 90 is 0. That means bigger the angle, right? Smaller the normal force actually, because cosine of theta starts becoming smaller and smaller and smaller, and it gets to 0 when basically the theta equals 90 degrees. And since friction is equals to coefficient times normal force, you can see, right? Basically, you know, in terms of like static, right? So that's why it actually, decreases. So, in terms of that. All right. But what we're going to do here is this. We can also see that, let's say these two equations that we get, these are the equations of the, this particular, example where object sliding down, it's speeding up, right? Down, like, and those two equations can give you how the, let's say, friction force, X component of gravity, Y component of gravity, normal force, how those are related to one another. So this equation can give you that. But there's also another thing we can do. For example, let's take this equation and let's say there are two unknowns. For example, I want to find kinetic friction. What is a kinetic friction? Okay. So let's say I can also see that, let's say if I don't have acceleration, right? In that equation, two unknowns, one equation, there's nothing I can do about that. Okay. But here's one thing we can do. Our experiment allows us to do this. As objects start sliding down, remember that one of the first experiments that we did, object going down an incline, and we measured the motion in terms of finding the position as a function of time, right? And plotting that, because what we can say is that if object starts from rest, so initial velocity is 0, then object as it's going down, you can measure the position at basically at equal time intervals. Then we can say that, all right, so then delta x is equals to v initial times time plus 1/2 at squared. Since initial velocity is 0, then we have equation just delta x equals 1/2 at squared. That was our first pivot lab that we did. That means any object sliding down an incline, I can measure the position as a function of time. Then how can I use that information, for example, to find acceleration? So what do you guys think? So let's say if I have a data where I measure delta x, where basically where I measure x as a function of time. So let's say when this is 0, this is 0. When this is 0.1, this is some x1. This is 0.2, this is x2, and things like that. What did we do? How did we use that information? Who remembers?
Well, x2 minus x1 for the delta.
Well, think like this. How can I use this information to find acceleration, for example? What do you guys think? That means I have a data table with position as a function of time, for example, and I want acceleration. How can I find that? I'm hoping at this point, after doing all those labs and analysis, you should be able to figure out that. What do you guys think?
For this one, I think we linearize the curve.
Linearize the curve.
So, because right now, if we're given like position versus time, that's giving us the velocity graph, and if we're finding acceleration, acceleration is just like the derivative of velocity. So I don't remember exactly, but I know for this one, I think we did something with linearizing the curve.
Well, I want to see if anybody remembers specifically what we did. Or think of it like this right now. You have a data table of, basically like this, right? You have a x and t. So you have t1, x1, t2, x2, t3, x3, and so on and so forth. What can we do with that data, or what can we do with that information if I want to find the acceleration?
Professor?
Yes.
I think in the lab, we got an equation that had a constant that was equal to the acceleration. or was it a component of acceleration?
And how did we find that? I mean, even like, let's say I'm waiting for somebody to tell me one thing at least that I'm looking for. So let's say you have this data. What do you do with that? How do you find the acceleration?
Is it acceleration is the derivative of speed? I mean, the velocity?
Well, it is, but how does it help me now?
We can graph the velocity and then take the derivative of it.
Okay, so, but do you have the velocity now?
Not yet.
You have position and time. Can you use that? If you're given this equation, delta x equals 1/2 a t squared, can you use that table with this equation and find the acceleration?
Yes, you get your final x and then you get your final time.
Well, remember, you have data table, right? It's not about initial or final. You have a data table, which is much more accurate than looking at just the initial and final. All right. So what you guys do here is you take this and you plot this as y equals m times x. And that's what we did in the first lab, first pivot lab, which means that we plot our x on the y-axis and our t square on the x-axis. So remember, so we did a graph where this is delta x, and this, remember, if we plot as a t, we would have had, let's say, a parabola like this. But then if you do t square, you linearize it as a straight line. But the idea here, what I was waiting for you or somebody to tell me, is that we take that data and we plot it in a graph where delta x is in the y-axis, t square is in the x-axis. Then I can use that, because think like this. If I plot this as delta x on the y-axis, t square on the x-axis, and I find, let's say, the slope, what is the slope of this graph then it would be equal to? What it be, what the slope would be equal to?
Acceleration.
Well, not quite acceleration.
Over 2.
Velocity.
No, acceleration. Who said acceleration over 2?
Me.
Justin, is it you?
Yeah.
Yes. It's acceleration over 2 because it's right there, guys. It's right in front of you. See, you have to be able to read this equation. If I'm doing delta x as the y-axis, t square as the x-axis, then whatever coefficient in front of the t square is then your slope. Means the slope is 8/2, your acceleration over 2. And our pivot labs give us the slope, right, of those lines. All you have to do is say then take 2 times that slope, usually given as, some a, right, constant a. So 2 times that, that's your acceleration. Okay. So that's what you do with this, type of data. Because if you have a data where you have position changes as a function of time, you can use that equation to plot. So that's why our equation was delta x equals 1/2 acceleration times t squared. And we could see, right, delta x was directly proportional to t squared. So if I'm plotting y equals m times x, where delta x is the y-axis, t squared is the x-axis, then the proportionality, right, this 1/2, which is basically technically a constant, is going to be your slope. So you don't have to any velocity, anything like that. Yes, we know a is dv dt, but a is also a number of other things. So right now that we were looking at from the experimental way of finding this. Okay. So this is what you have to do. All right. So now let me show you the experiment. So maybe it will help you to kind of put things, in perspective. So. All right. So in this lab, we're going to apply knowledge of Newton's laws in kinematics to determine the coefficient of static and kinetic friction. All right. So first we start with, you can write again, Einstein on the ramp. So we have a video shows our Einstein figure, Action figure is sitting on a slab of wood coated with plastic tape. Einstein has a rectangular metal magnet attached to his back, which is used, in other experiments to keep the action figure in place. In this experiment, it serves as a smooth sliding surface. Okay. So our goal is to use this video to determine the static and kinetic coefficient of friction. Okay. So, and here's the experiment. So basically right now, starting with the flat surface, you can see, right, increasing, and you can see, right, as we increase the incline angle, the, Einstein, which is our object, is still at rest. And the reason that because right now, static friction is able to cancel the, x component of gravity, because in this case, I still have this, right? This is my coordinate system. See, what I have here is, there's gravity, here's friction, here's normal force. If I look at then gravity has two components, x component and y component. Y component is canceled by normal force. In this case, x component of gravity canceled by friction, because friction is strong enough that it's able to keep the, let's say, object at rest. But x component of gravity is equals to mg sine theta. That means as we start increasing the angle, x component of gravity becomes stronger and stronger and stronger and stronger, until at some point you're going to see, right, we're going to reach some angle, which is the critical angle, beyond which the object's going to start sliding down, because, as this starts increasing, so technically static friction cannot go beyond some maximum value that it will reach, and gravity will win and it will start sliding down. So you should be able to then see that here. There you go, we're getting closer and closer. We reach critical angle and then it starts sliding down. All right. That means in a way you can see that what we can do in this example, right? So take a protractor and we can just put it here and be able to see that, all right, so now it's 0 as it's increasing. So then you see at some point it starts sliding down. So you go find the angle right before which it starts, see, let's say somewhere over there it starts sliding down, but here it's still at rest. So somewhere over there you then will accurately measure the theta that, gives you the critical angle, right? You can see that, right? So here is critical angle, here's beyond critical angle. It starts sliding down. Okay. So this is how you would find the coefficient of static friction. As I showed you, right? Coefficient of static friction, you need to find the angle theta where the object right before it starts sliding down, somewhere over here, and then use that to find the static friction. For the kinetic friction, then we're going to start from here, and then, okay, say, all right, so this is when objects start sliding down, so I'm going to start here, and I'm going to take a, all right, so let's say take a stopwatch, right there, and go find the instant when it starts sliding down, which is right there. Reset, take the ruler, change its orientation, so it matches the incline angle. So technically I don't need this anymore. So then let's say one thing you can do, you can start with the, feet. All right, so let's say right there. And you will be then here at the bottom measuring those two measurements. So let's say what we're going to do here is this. Let's say you can see, right, this is where Einstein is going to start sliding down. So my timer is set to 0. So if I start my timer, I'm basically looking at this bottom of his feet, right? So then you can say, then it starts sliding down. Then I stop, go and get my 0 right there. And I can say, all right, so I'm going to make a table where this is going to be position. In units of, I'm pretty sure it's centimeters, right? Yeah. So let's say this is variable X. So you can say, all right, so this is 0 when time in seconds and the variable is t is also 0. All right. So if you want, you can just start measuring things in centimeters and then convert it into meters. Because when you're dealing with newtons and things like that, you have to be, you know, always in units of length, in meters and kilograms and things like that. And then from here, you can see, right? So you basically go and reach the bottom. Where are the feet? So let's say somewhere over there in about 4 point something seconds. So you want to have a good data. So maybe we can take this in terms of, let's say, not every 0.1 second. Because if I do 0.1 second, I have only like 4 data points. Maybe 0.5. Let's see if we can get that. So if we can get that accurate. So let's say 0.5. All right, I think it goes 0.33. All right, it seems like it allows me to go in terms of this 0.333, right? So I can maybe use that. So, or maybe like, let's say, you know, I guess 4 data point is good enough for us. So let's go to 1. So what do you guys read? So what will be the reading if it's 0.1 second?
One centimeter.
No, it's not 1.
0.3.
Well, it's a little bit more than 0. So does that, you know, dotted line is what? What are those dotted lines?
0.5.
0.5. And in a way you can see, right, it's almost touching that 0.5. See, I can maybe like zoom in. See, it's almost touching it, right? So in a way I can say 0.4 or 0.5, but not 0.3. So let's say I can say, you know, all right, so position 0.4 when time is 0.1 second. All right. Then we go when the time is 0.2 seconds. So what do you guys read?
$1.6.
I think it's more than 1.6.
One-
0.9.
Like 1.8 or
I would say maybe 1.7 or 8. That's a little more reasonable. But not 1.6. Again, you have to be a little more accurate in this case because you don't have enough data. So maybe 1.7, let's say, when it's 0.2. Even maybe 1.8 would have been more accurate. Then let's say we go to the 0.3. What do you guys read?
Looks like 4.
Yeah, I think maybe we can estimate that it goes a little bit, you know, beyond 4, maybe like 4.2 or something like that. So, because it's so fast, right? So I would say 4.2 maybe, and that's 0.3. All right, so then the rest you can do that. But I already have enough data. So when I come back over here, see if I do position versus time. All right, time. All right. So is this a linear graph?
No.
No, it's not. Remember, because position is not proportional to time. It's proportional to time squared. So technically I can do this, fit this, and you can see, you know, this is what you're getting. And so what will be the acceleration right now? All right, so what is the slope? Let's start with that. What's the slope?
A.
No, slope is not 8.
Oh, no, A, not 8.
Oh, A, yeah, thank you. So A is correct. So A is the slope and this is your slope. Is that our acceleration?
Half.
Half of it, exactly. This is half of our acceleration. So acceleration should be then double this value. Let me see if I want to do this. Maybe I want to double check if it's going to be too different. So remember, I can, no, not that. Let's say if I go and make another one here and say it's time squared. And let's say formula is time times time, same thing. So there you go. So this is the time squared. So let's say if I want to look at the A here is 46.33. So what I'm going to do, I'm going to replace time with time squared, so I have a linear one. Obviously, this is not a good right curve for that, so we go linear, and we get that. See, I get exactly same slope. But the idea is that, you can, linearize it like this, or you can actually find the correct curve, right? The right curve, which is in this case quadratic, and you're going to get exactly same slope. Because when you find the correct, curve for your data, it basically still, this data tape, this software, gives you the correct slope regardless. That means what we have here is, that's, A, right? A is basically my, my slope, and it's equals to, half of A. So then, we can use that to get the acceleration. And then the rest is basically some questions. It says, use the measurements and observation from video to determine coefficient of static friction. And then use the measurements from the video to determine the coefficient of kinetic friction. So either you have to very, basically carefully describe all your steps, how to do that by typing here, or just do on another piece of paper, all the work, and then just take a picture and upload it here. But I want to see all the work that, you have to do in order to get the static and kinetic friction using all the observation and data that we get from this, experiment. Right, any questions? All right. Wow, it's already almost an hour. All right, guys, so that's basically our experiment 6. So it will be due next Tuesday. So this Thursday we have the lab, and then basically you have weekend to work on that. I will try to get chapter 7 or chapter 6, forgot already. What was the last chapter? Chapter 5, right, that we covered?
Yeah.
So on the exam, yeah. So I'll try to get chapter 6 lecture video posted so you guys can prepare for next week. Hopefully, I'll try to get that before next Tuesday class. But, since technically there's nothing much, from Thursday to Tuesday, so you have enough time to work on this lab. Also, this lab allows you to kind of see all of those things, visually, right? So how the object going down and all of those things, I recommend, if you find time, to at least, kind of play with this lab, because it will let you to, look at all of this from the, experimental point of view. All right. Let me then take maybe next 15-20 minutes, just basically give you the summary, like let's say key points of, last 5 chapters in terms of like what we, covered, what you should, make sure to know, and all of those things. And then I'll give you time for the practice exam.
Professor,
Go ahead.
I was just going to mention, in the lecture video, you talked about the resistant forces, but you didn't really go over any examples or anything. Is that something that we have to, or is that going to be like on the exam, like any like solving questions?
If you're talking about, let's say, so technically friction also a resistive force. Okay?
Oh, well, the air resistance.
But yeah, in terms of those, it was mostly for your information. So I don't really go into greater detail on those. So
Right.
yeah, I mean, that's something I cover, but I actually good observation. So technically I don't do any examples and things like that. But I think, wasn't there any homework on that? I thought I assigned a homework on, on the resistive force. On chapter 5 homework. Wasn't there any?
I haven't called it yet. I'm not.
All right, so guys, make sure you guys on top of the homework problem, because the homework is the best source for you to learn, how to solve problems and things like that. But yeah, I don't really go too much into this resistive forces. Yeah. So mostly, friction. I make sure that you guys really know the friction and things like that, because we have a lab on friction. We had like a recitation on frictions. I talk about a lot about frictions and things like that. So expect, friction to be a big part of the exam 1, right? All right, so then let me just basically here. do that. All right, so let's say, so the chapter 1, kind of like, let's say the key points from chapter 1. From chapter 1, we had vectors. So remember, basically vector was kind of like how we started, our, learning about physics, that we have this quantity that had magnitude as a direction. So make sure you understand the vectors versus scalars, let's say, and what is the difference between them, and also how to do, let's say, vector calculation and all of those things. So let's say if I give you several vectors, vector A, a vector B, for example, right? And ask you to find the resultant. Vector C is, let's say, the resultant. You should be able to say, all right, so if you add vectors A and B together, so you have to be able to, calculate that. So who remembers what do we call, which approach should you take in order to solving this resultant? How would you solve this result? What is it?
Components, like, because graphical method would be with 2 dimensionals will be more difficult. So wouldn't you have to find the components of A and B and then add those?
Exactly. So remember, one thing we have here is the graphical method is actually a very useful way of, predicting your result. See, for example, I can, since both of them already connected to their tails, I can then kind of construct a parallelogram, right? And then, draw the resultant. This is my vector C. Now you can see that this is my vector C, like, let's say, using this, the diagram. And even though I don't know exactly the value of C, let's say I don't know its magnitude or its direction, but I already have some information. You can see, right, vector C is less than magnitude of A or B. That means you should expect the magnitude. So let's say if this is 5 and this is 6, I would expect maybe, all right, maybe other way. Maybe this is 6, this is 5, because I have the length, right? Maybe this should be around 4 or something like that, right? Because this is, less than even vector B. So that can also, graphical method can give you what to expect. Because, if I find magnitude of vector C and I get 20, that makes no sense. This would have been 20, right? This would have been 20, and I'm not getting that. So I'm getting something that probably, around 4 or something like that. Also, what should you expect for the direction of the vector C to be? What should you expect for the direction? Like, estimate it, looking at this.
Like,
what is it?
Do you mean like degrees?
Yes, degrees.
Like 300, 320, 330.
Yeah. So basically, if you go like this, maybe 330, right? That's perfectly reasonable direction estimation for me. Yeah. Because think like this, when you're doing the calculation and you get, like, let's say 120, well, this should be like a red flag, right? You probably did something wrong because your vector C is in the 4th quadrant, right? And it should be between, 270 and 360 for sure. And then you should get, like, let's say, more precise value once you calculate component of, vector C, X, and Y, and then do the inverse tangent.
Professor?
Go ahead.
So if it asks for find the angle from a positive x-axis, could we say either 330 degrees or could we say negative 30 degrees?
Yes. Yes, if you say negative 30, let's say with respect to x-axis, that's fine with me. So because when you say negative 30, I right away assume this negative 30. But if you say negative 30 for this one, I will never assume that's negative 30. So you should be, let's say if you say negative 30 with respect to negative x-axis, then maybe I will, you're giving me enough information to know where the theta is. But if you say, okay, theta is equals to negative 30, the only angle of negative 30 I will expect is this guy over here. Yes. But if the theta is already with respect to, positive x-axis, you can do it either 330 or negative 30. That's fine.
All right.
So yeah, so in terms of then these vectors, right, remember, so if you have 2 vectors on the same axis, you can add them together. you have two vectors that are perpendicular, you can use the Pythagorean theorem. But if you have a vectors like this, then you have to use the component method. Try to always get the graphical approach first, and then using the table, and then finding the calculation, all the, basically your goal will be to find the component of the resultant, and then finding the magnitude and direction of the resultant. Right, because when we went to chapter 2, we then learn about all the other quantities that are, basically are vectors. So we learn about displacement, which is a vector, and that's, x final minus x initial. And then we learn about then velocity, right? So velocity, you can talk about average velocity, which is delta x over delta t, which is the rate at which you change your position. So let's say if you go x initial to x final, let's say how long did it take? So how fast were you moving on average? So that's also a velocity, that's also a vector. Or we can find, let's say, okay, so then this equation gives me average velocity between those 2 points for the entire trip from x initial to x final. Or I can look at, okay, so how about somewhere over here, some x? How fast were we going over there? Well, in order for me to get that, I need to then find the derivative of x as a function of time and find the rate at which, this is instantaneous velocity, remember. So basically dx dt. That means anything instantaneous, you have to take the derivative for that. All right. Then we talked about 2 types of motion. There is uniform motion. The uniform motion was that we are moving at constant velocity, which means our v2 minus v1, let's say, was 0 because v2 is equals to v1. So v is constant, which means then you are moving at the constant rate. So if I plot that motion, x versus t, we would get a straight line like that. All right. And equation that shows me how those things are related for a uniform motion will be then delta x equals vx times time. And this is the reason I put vx, not average v, because there is no average v. All the v's are the same. So that's the equation for the uniform motion. So you can say, all right, or delta y equals vy times time. But still, if you're moving in a vertical direction at constant velocity, you can also do this. So technically then uniform motion assumes one thing. There is no acceleration in that, for that motion. That means you're not speeding up, not slowing down, not changing direction. Then we looked at non-uniform motion. Which basically tells us there is acceleration. So acceleration then average equals delta v over delta t, because now delta v is not 0 anymore. And we can say also there's an instantaneous velocity, instantaneous acceleration, which is dv dt. But since v is dx dt, then you can say acceleration also d square x dt. Then we looked at special case where the acceleration is constant. That means the rate at which you change your velocity is constant, which allows us, since acceleration is constant, allows us to get those kinematic equations. Then we had those 4 kinematic equations. V final equals V initial plus AT. Then X final equals X initial plus V initial times time plus 1/2 AT squared. Equation 3, V final square equals V initial square plus 2 times A delta X. Equation 4, delta X equals V initial plus V final divided by 2 times time. So we got this kinematic equations if the acceleration was constant. So this was, in chapter 2, was like one-dimensional kinematic motion. But then we also learned that, you can technically have this as in terms of same equation can be applied for a 2-dimensional motion if you break your motion down into 2 separate components. But then we could use this, right, to figure out how far the object moves as a function of time. Let's say, what is the final speed? What is the acceleration? How much displacement of the object if it's moving at some constant acceleration with some velocity and things like that. With anything kinematics, right, assuming there's a constant acceleration, we use then these equations. So from the calculus point of view, again, kind of like summarize this, you can kind of do like this. So if you have position, velocity, and acceleration. So then going from position to velocity, you take the derivative, dx dt. Going from velocity to acceleration, again, you take the derivative, dv dt. But then we learned that you can also go from acceleration to velocity, which was then the, basically the delta, delta v is equals to integral of a dt. So you take the derivative. Or you can go from velocity to acceleration, which was then delta x equals integral of v dt. So assuming that velocity, let's say if the velocity was given as 3t squared, right? So you can just go and say, all right, 3t squared dt, and then take a integral and then find the displacement. That means you have to understand that those are the ways to go from position to acceleration, that taking derivatives, or from acceleration to position, you have to then use the integrals. And if you're doing the position versus time graph, then your graph will always be a curve like this if it's a non-uniform motion. All right, so one other thing we learned in chapter 2 was free fall. So free fall was object motion due to the Earth gravity, where it has a vertical acceleration of negative g, where g is 9.8 meter per second square, and it was fixed. That means every time you have an object that is being dropped or thrown, or like throw upward, throw downwards, things like that, the object basically moving only due to the influence of gravity. So this is what we call free fall. And free fall means that you can also go from 1D or 2D, right, where the two-dimensional was known as a projectile. So you have object going down like this, up or down like that, or with some velocity like this, or with some velocity like that. So those are the difference between one-dimensional or two-dimensional free fall. One-dimensional goes straight up or straight down. Two-dimensional means that it moves such that it's a projectile.
Professor?
Yes.
What would be the best way to identify in a question whether it's asking for one-dimensional or two-dimensional kinematics?
You want to look at if there is some kind of horizontal component to velocity. So because remember, when you go into two dimensions, you have this, right? So think like this, you have r, which is the position, x I hat plus y j hat. So, and if you're looking at change in position, then becomes delta x I hat plus delta y j hat. Then you have a velocity, where basically you have an x component and you have a y component. Okay. And then you have an acceleration, which is an ax I hat plus ay j hat. So this is general two-dimensional. Because if you have a two-dimensional, that means you are looking at how the x direction changes, how the y direction changes simultaneously. In a free fall, you basically start like this. So free fall means acceleration, if you're doing ax I hat plus ay j hat, so it goes like this. There is no horizontal acceleration, but then negative g vertical acceleration. So this is a free fall. Then velocity becomes then Vx I hat plus Vy j hat. So then think like this. So if I'm kind of doing this. So if it's 0 I hat, then minus gj hat. So then you can see, right? If we're considering then the acceleration in a x direction being 0, right? Acceleration to be 0, that means this Vx here is nothing but constant, because you need acceleration to change this Vx, right? There is no acceleration. Then this gravity, acting only in a y direction, so then in a y direction there is ay, right? That means Vy will change, which means then you have this ax, sorry. So if I'm looking at the position change two-dimensional, so this will be then delta x I hat plus delta y j hat. Okay. Now that means this is what you have for the free fall. This is for the general, let's say this is general equations for the free fall. Now, if it's two-dimensional, right? If it's two-dimensional, that means you are basically using both horizontal and verticals. Okay. That means, for example, if you have an object that's going to undergo a two-dimensional, let's say free fall, so that means it has to have both x and y component for the velocity. That means it has to be given. It has to have both x and y component, or at least an x component. That's the difference, because one thing you can have, see, this is the velocity. So that means, imagine there's a ball sitting there, you just kick it with that velocity, so it goes like in a free fall like that. So then if I take that, if I break it down, right, if I break it down, you can see, right, there's an x component and there's a y component initially. Okay. So, or if you have an object kind of that goes off the cliff or something like that, and you can see, right, velocity, now it has an x component initially, but no, y component initially. Okay. But still, the two-dimensional free fall, you have an x component velocity. Either x, it's entirely in the x direction initially at t equals 0, or it has a component. So again, this motion here is, basically in a free fall. That means think like this. If you have a velocity that has an x component and y component, right? And the acceleration, it's 0 I hat plus ay j hat. So if those two kind of together, then you have a two-dimensional. Okay. Because you have both x component and y component. But again, even if you have no y component, there has to be an x component for the initial velocity, or it to be a projectile. Because one-dimensional free fall means this: object has the same acceleration, which means 0 I hat plus, let me do this here as minus g. So minus gj hat, but the velocity is this: 0 I hat plus some initial of some vy j hat. Okay. That means one-dimensional free fall when those two are 0. Which means that there is a vertical acceleration due to Earth's effect, Earth's gravity, right? And then object either will have initial velocity or will not, but there will be some velocity in the y direction. Because remember, for the one-dimensional free fall, you can just drop the object, right, and go straight down, or you can throw the object and it goes straight up or straight down, but that means the motion is along the vertical axis only. But when you are doing two-dimensional, there's always going to be the x component, so either going to be like this or like that. That means there will always be some kind of horizontal range as well, where in a one-dimensional there is no horizontal range. It goes straight up and straight down. That means your x, right, delta x equals 0. There is no delta, there is no delta x. Why delta x equals 0? Because there is no Vx. Vx is 0, so your x position doesn't change. All right, any questions? All right, so remember, that's kind of like what we have with the projectile, right? So there's, two types of projectile. Either you're given some initial velocity with some launch angle theta, so then you go like that, or you basically go, horizontally first and go straight down. So that means what you have here is this. So this is V initial x I hat plus V initial y j hat. That's a non-zero launch angle. That means that your projectile has some kind of launch angle. Where if it's a zero launch angle, then V initial vector is equals to V initial x I hat, but plus 0 j hat. It has no initial vertical component. So V initial in a y direction is 0 if theta initial equals 0. All right, so from chapter 3, so this is already chapter 3, right? So from chapter 3, we'll also learn another thing, which was a relative velocity. Which means, like, let's say if you have an observer 1 and there's a car moving, let's say this is 1 and this is 2, and then maybe there's another car, right? And that's, let's say, 3. So, and let's say you have a velocity of 2, velocity of 3, right? So basically the car 1 is moving, car 2 is moving, car 3 is moving, person 1 is at the rest or something like that. Then you can find their relative velocities because there is no absolute velocity. Whatever car 2 speed is cannot be described by 1 and 3 with the same amount, with the same quantity, with the same value. So because velocity of 2 relative to 1 is not equals to velocity of 3 relative, velocity of 2 relative to 3. Because 1 is at rest relative to 2, but 3 is moving relative to 2. So their velocities will not agree because they have different relative velocities. Remember, what we do here is we have a notation, right? Where you can say, all right, so velocity of 2 relative to 1. So we have this 1, 2, and 3. So the notation goes velocity of 2 relative to 1 equals, then velocity of, we move it here, 2 relative to 3, then plus velocity of 3 relative to 1. That was the notation. Or let's say velocity of 3 relative to 2 will be velocity of, you move this one here, 3 relative to 1, then velocity of 1 relative to 3. Where the inner ones, right, are the, third object, and you have to use then 3 different objects to get the relative velocities. Right. So we talk about this in chapter 2 and chapter 3, because we have a 1-dimensional relative motion, we have a 2-dimensional relative motion, where, in terms of 2-dimensional, you are looking at the vector sum. So 3, 2 is equals to V 3, 1 plus V 1, 3, right? The same thing. But, if they're not on the same axis, you have to actually find the resultant using the, Pythagorean theorem and so on and so forth. Make sure you guys review this as well. And then finally, we go to chapter 4 and 5, which are basically application of Newton's laws of motion. All right, so I imagine that's the freshest in your memory. So we have, the first law is equilibrium, right? Where the net force equals 0. Means that we are looking at the net force in the x direction equals 0, net force in the y direction equals 0, which we learned that it means that this is in equilibrium, object in equilibrium, which there's no acceleration, there's a constant velocity. So object in equilibrium, either at rest or it is moving at constant velocity. And Newton's first law tells you that if the object is at rest, it's going to remain at rest. And if object is moving, it's going to remain moving at constant velocity because we are assuming that all the forces on it cancel each other. So then let's say if there's a chandelier hanging, or there's like a lamp hanging, or there's an object hanging, or something at parked, or something like that, those are example of, equilibrium. Well, all the forces, cancel each other. And you have to kind of assume that by carefully understanding those keywords, right? Parked, hanging, suspended, all of those things means that object is in static equilibrium. You can also be in dynamic equilibrium. So what is the keyword for you to understand that object is in dynamic equilibrium? Who can tell me that?
Constant acceleration.
No.
Constant
Constant
velocity.
acceleration is, means that it's accelerating.
Oh, I mean no acceleration, but constant velocity.
Exactly, constant velocity. That means if object has a constant velocity and you're told that it's moving at constant velocity, well, remember, constant velocity means acceleration is zero, because we need to make sure that acceleration is zero. So if object is moving at constant velocity, it means that no acceleration. So it is dynamic equilibrium. So think like this, right? You can have velocity zero and acceleration is zero, or you can have velocity is not zero, right? Some constant velocity, but acceleration is zero. This is static equilibrium, then this is dynamic equilibrium. Both cases, net force is equals to zero, okay? Net force is zero, so you can always assume that all the horizontal forces cancel, all the vertical forces cancel each other. Second law is basically give you, condition when there is no, equilibrium. So net force equals mass times acceleration. Again, what we do here is we understand that you are dealing with two dimensions. So you can say net force in the x direction equals mass times acceleration. And net force in the y direction equals mass times vertical acceleration. So kind of break down your motion into x and y. And remember, these are just factor sum, right? So you have to use those three-step approach. So this is free body diagram. Every time do the free body diagram. Step 2, then use a force table. So then 3, use the force table to set up your equation 1 and 2, which is net force in the x direction and a net force in the y direction, right? So, set up those equations. And then let's say step 4 can be if you want to find the net force, which then will be square root of x component square plus y component square, and finding the theta for the net force from the inverse tangent of net force y over net force x. That means you are basically treating this as like a vector sum, right? Vector sum of all the forces that you have acting on the object. But this 4-step approach can help you a lot by minimizing all the type of errors and things like that. That means looking at all the forces separately, putting them in a free body diagram, labeling them, giving the direction, everything correct, then organizing them in a force table with all the signs and everything correct, then using them to find the equations. Okay. All right. Then technically chapter 5 basically gives you also the third law. That was action reaction, right? So any two object, basically F21 equals F12 in magnitude but opposite direction. That means every force has equal but opposite reaction force. And this is, let's say generally when you have two objects, let's say in physical contact, see, because they're in contact, here's a force where this is 1, this is 2, like basically force that 2 exerts on 1, well, the same force that 1 exerts on 2. If two objects are connected by a rope, right, or something like that, they're interacting, so you can say that acceleration of 1 and 2 are same, and then the tension between them is also the same because it's the same rope. Here we use that massless string approximation. We say, remember, mass of the string equals 0, then we can say that tension is constant. Constant means that on the same, if it's the same rope, tension is same everywhere. See, this is the same rope, that means the tension is the same. If you have another rope, another mass, then this is T1, this is T2, because two different ropes, and they're never the same, okay? But if you have tension along the same rope, always going to be the same, because we're using the massless string approximation. All right, so the last, I guess, very briefly go over the friction, which, the latest thing that we covered, so it should be relatively fresh in your memory. So you have static friction, which has a maximum value. This is equals to mu s times normal force. And there's a kinetic friction, which is mu k times normal force. And we also learn about net force in a centripetal net force, which will be equals to speed squared divided by r. So those are the, couple of, important things that you guys need to know from chapter 5. Again, those resistive forces, like let's say air resistance and things like that, I don't really go over that so much in terms of the testing you on that. So I talk about that a little bit, so you know that, but not necessarily being tested. But in terms of then the friction, understand, right, when you're dealing with static friction, when you're dealing with kinetic friction. In terms of centripetal force, understand that there are vertical circular motion and then horizontal circular motion, and be able to, understand how to work with each one, right? So when you have a vertical, gravity at the bottom and at the top is a centripetal force or part of a centripetal force. But if it's a horizontal, gravity always acting down, so it's never a centripetal force. So that means you have to have something else. Also, if you have a banked, so you have banked or unbanked roads. So I talk about that also in a lecture, in a video lecture. So make sure you understand the difference between banked and unbanked road, and how to find, the quantities like, designated speed or the banked angle and all of those things. All right, any questions?
Professor,
Yes.
you said in the horizontal circle, there's no centripetal force?
No, I said gravity is not a centripetal force.
Mm.
Because gravity always acts. Remember, centripetal force is the one. So let's say if your object is here and this is the center, so you draw a radial line, and any force along that radial line is a centripetal force. So see, gravity, even though it's acting in the opposite direction of the center, it's still along on that line, so it is a centripetal force. So let's say if there's a tension there, right, then what you do is T minus mg is equals to mv squared over r. We talked about that last lecture quite a lot.
Okay.
So, but in this case, if this is the string, see the tension here toward the center, but gravity is perpendicular to that. So it's not a centripetal force. All right. Any questions?
For the multiple choice questions, is it mainly vocab stuff?
Could be some simple calculations as well.
Like conversions?
No,
Or-
like let's say calculation of problems for which I don't need to see the work. Let's say basic plug and chug stuff.
Okay, thank you.
Professor, I do have one quick question with chapter 3. I noticed that we use a lot of the circle stuff in chapter 5. I got kind of confused with the centripetal acceleration and radial acceleration, because there's instances where they ask us to find radial acceleration and we use the equation for centripetal, but then we're also told that radial acceleration is negative of centripetal acceleration. So I'm just kind of confused on that topic.
Okay, so imagine here's your object and it's going around circle like that.
Mm-hmm.
Oh, let me try again. Right, like that. So this is the center, right? So let's say this is a ball connected at the end of the string, right? And you rotate the string like this.
Mm-hmm.
All right, so the tension will be in this direction, right? This is the tension force. Now the radial, see, going from the center, I can draw this what I call a radial, what we use r hat like that. It's a radial unit vector. So then acceleration radial is, you can see, right? It means any acceleration along that radial line. And centripetal acceleration is along that radial line, right? But you can see, right, it's pointing in the opposite direction of the r hat vector, right? So that's why there's a negative there. Negative just means that it's in the opposite direction of that r hat. So kind of like this. Because r hat vector is always from the point of, let's say, from the central point, right, toward the object. So you draw a line from where the center is to the object, and that's your r hat vector, radial line pointing in that direction. Think like this. So let's say you have a coordinate system x, right? So let's say this is your position x. So then you can say that, for example, then this is going from the origin, your reference point, because here the center is the reference point. So this is, you can say this is, you know, I hat, right? Or r hat, right? So you mean radial in that direction. So technically then you can say that the I hat and r hat are exactly the same, right? So do you agree if this vector is in this direction, if I have a vector in this direction, that's technically it's negative I hat, right?
Yeah, yeah.
Which is also then negative r hat, right? And that's what this is. It just means that it's in the opposite direction of my unit vector direction, which is always starts from the reference point, which is the origin.
Okay, okay, thank you.
You're welcome. All right, guys, so let's do this then. Let's, you know, if no more questions, I'm gonna go ahead and stop. Take the next 30 minutes. I'll break you into groups if you wanna work on the, you know, practice exam 1. Again, if you already completed, you guys are free to leave. But, you know, if you haven't, this is your chance to work in groups. And we have Paula here as well, right? So you guys can work together, try to get those done. Remember, those are extra credits, so just kind of like a free point, right? And you're doing something that helps you practice, plus you get basically some, you know, both practice and extra credit. All right, so here, let me create those. All right, so the next 30 minutes take working on those, you know, practice exam.